So in this video, I'm going to discuss continuity. Now, continuity is something I discussed briefly before, but it basically just means that the function is very simple in terms of its values and limits. The value and the limit agree is basically what continuity means. So think, for example, of f of x equals x. What is the value at 2? Clearly, if you plug in 2, you get out 2. Very easy. What is the limit at 2? And here, notice I'm not talking about a handed limit, right? Not left-handed, not right-handed. I'm talking about just the limit, and what is that? Well, you take the left-handed limit, which is 2. You should easily be able to verify that either sequentially or graphically, whatever. But the left-handed limit of x as x approaches 2 is 2, and the right-handed limit is also 2. So all three quantities, right? I've said before that you are always interested in three quantities, the left-handed limit, the right-handed limit, and the value at the point. All three of them say the same thing, 2. That's what continuity means. All three of these things say the same thing. So in fact, it turns out, and the value of this is that if you know a function is continuous and you are asked the limit, you don't have to actually bother with the limit. You could just plug into the function. So for instance, every polynomial is continuous. And that means that if you're looking for the limit of a polynomial, you might as well just plug into the polynomial. So polynomials are continuous, and therefore the limits are easy. You just plug in. Sines and cosines are also continuous. So if you're asked to find the limit as x approaches pi over 6 of sine x, you just plug in pi over 6. Sine of pi over 6 is equal to a half. Likewise with cosine, and also likewise with 2 to the x and e to the x. These are continuous, by which I mean, so we could talk about continuity at a point, in fact. Being continuous at a point means that at that point, the limit and the function values agree. Now, we say that a function is continuous, full stop, right? Not at a point, but just is continuous. If it's continuous at every point, right? So by knowing that a function is continuous at every point, you know that every limit can be found just by plugging in. Here are some functions that are not continuous, which just means that they're not continuous somewhere. Take, for instance, square root x. Now, this is continuous almost everywhere. It is continuous at 1, it is continuous at 4, it is continuous at 2. At all of these points, it is continuous, and therefore you can plug in, right? You look for the limit as x approaches 2. Well, it's just square root 2, right? You just plug in, except at 0. 0 is the exception, and that's because square root x doesn't have a left-handed limit. We could go ahead and plot square root x, and it looks like this. It does not have a left-handed limit, and therefore it's not continuous at 0 because the left-handed limit does not agree with everything else. So square root x is not continuous at 0, and it's not even defined, and therefore also not continuous for negative numbers. We can say a lot of the same kinds of things about 1 over x. So it is not continuous at 0, although it is continuous everywhere else, even for negative numbers. If you recall the graph of 1 over x, in most of its parts, it is a nice, smooth, connected graph. There are no weird parts. The only weird part comes at 0. So that's the only point of discontinuity. In general, when you're looking at the graph of a function, any gaps or tears is what really discontinuity means. So if you look at the graph of ln x, as we saw in a previous video, it is continuous everywhere except at 0 as well, because there it flies off to negative infinity, and it's not even defined for negative values. So these functions are continuous in most places, and in fact they are continuous, at least these two are continuous everywhere that they are defined, right? Because these are defined for positive values, and at every particular positive value they're continuous there. They're just not continuous at 0, and that's just where they're not defined. The square root x is a little bit different because it is defined at 0. It is equal to 0 at 0. but it's not continuous there because it doesn't have the left-handed limit. Anyway, so as I said, the geometric statement of what continuity means is that there are no gaps or tears. Let's also say what the so-called analytic version of continuity is. It says that the left-handed limit is equal to the value of the function is equal to the right-handed limit. So this is what we sometimes call the analytic statement of continuity, but there's a geometric version that I've already mentioned. Now, this is often useful when you also combine it with the fact that limits distribute, and you have all of these rules for limits. These rules are kind of hard to read, and the formal statement has to assume that every limit written here exists. But basically, they just tell you that to find the limit of a function, you can just find the limit of the parts of the function. So, you know, for instance, when we did this example, if we want to know what the limit of the function is, and we wanted to use that rule, we could say that it's the same thing as if I found the limit of just x squared, and then I found the limit of x, and then I found the limit of 5. And I put them all together, right? So that's just evaluating the limits of the parts, and then putting the parts together to get the overall limit. That's more or less what these rules tell us. Now, notice that that's not always true, because this limit, as we know, does not exist. And if we tried to find the limits of the parts, we could do that, right? The limit of 1 is 1. The limit of x is 0 as x approaches 0. And yet, this limiting value is not 1 over 0 because that's not actually anything. So, that is the first thing that I want to say about continuity is that when a function is continuous, it's very easy. You just plug in, and especially when you can sort of like distribute to all the parts and evaluate all the limits of all the parts, the whole process is very easy in that case. The hard part comes from discontinuities. That is pretty much always the hard part of finding limits, is finding limits where there's a point of discontinuity. So we will discuss some ways of handling discontinuity. I mean, the sequential method is a way of handling discontinuities, right? You plug in points close to the x value and see where the y value goes. That's one way of handling discontinuities. So is the graphical method, because in the graphical the videos that I made before about the graphical method, you saw already how we look at points of discontinuity and decide limits in that case. And so the points of discontinuity are always the hard parts. And so here I will discuss the algebraic way, or one of several algebraic ways, of evaluating limits at points of discontinuity.